This is Dr. D. Govardhan, Professor at Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are covering shear force and bending moment diagrams. When a horizontal beam, it may be cantilever, simple supported, or overhang the beams. When it is loaded with the vertical loads, it deflects or the bends because of action of the forces. The amount of deflection it takes place depends upon the type of the loads, length of the beam, elasticity of the beam, and type of the beam also. The scientific way of studying the distribution of the shear force as well as the bending moment diagrams is most important to find the deflections as well as the effect of shear force and bending moment diagrams. The shear force means it is a resultant of the vertical forces or the perpendicular forces which are acting on the beam. Sometimes it is also called the unbalanced forces which are acting on the beam when you considering toward the left hand side or right hand side at that point is treated as shear forces. The bending moment generally it is written as Bm. At any section is defined as the algebraic sum of the moment of all the forces which are acting on the beam with respect to the left hand side or right hand side of the given reference point. The beams are classified based on the whether it is a fixed one end or two ends, or depending on supports which are keeping that beam in horizontal positions. These are cantilever beam, simple supported beam, overhanging beam, rigidly fixed or built-in beam, and continuous beams. A cantilever beam. It is known as ear cantilever beam. The cantilever beam is the beam which is fixed at one end and the other end is free now. But the beam should be always in horizontal position. The second one is simple supported beam. A beam which is freely supported at both the ends as shown in figure is known as simple supported beam. The term freely supported implies that the end supports exerts only the forces upon the bar but not the moments. That is the moment at A and B equal to 0. That's why we are calling these are free supports. But here the reaction is there now. That is the forces are there now. Moment is 0. Overhanging beam. The beam is similar to the simple supported beam, but it is extends behind the support on one side or it may be two sides as shown in figure. Fixed beams, the two ends of the beams are fixed, are built in walls, is known as the fixed beam. The beam is shown in figure. The beam is also known as built-in or encasted beam. Continuous beams. A beam which is having more than two supports entire its span, then the beam is known as a continuous beam. Here it's shown in figure. And a cantilever simple supported beam. Here the word, it is a combination of cantilever and simple supported. Here cantilever beam is the beam which is in which one end is fixed, other end is free now. But here in cantilever simple supported beam, one end is fixed, other end is freely supported as shown in figure now. That means the moments at this point is 0. Here earlier discussion, when the beams are subjected to the vertical loads, it deflects now. These loads are classified into point load. The point load is also called sometimes concentrated load. That is, it is represented like this. That means the area under this load, it is infinitely very, very small, or in other words, it's concentrated into one point. The second one is uniformly distributed load. That is, the load is distributed over the length of the span according to the certain rate now. That is, it may be here W per meter length. Like that now. Uniformly varying load now. That is, gradually that load is varying from one end to other end on length of the beam. The type of load is called uniformly varying load. So here now, one is the point load, the second one is uniformly distributed load, the third one is uniformly varying load now. Here sign conventions. Here earlier when we discussed now shear force and bend moment diagrams, the shear force is the unbalanced vertical forces which are acting on a beam is called shear force. At that section we are taken now. But some forces may act downward direction, some more forces are acting upward directions. So based on this direction, some forces are treated as positive, some more forces are treated as a negative now. Here, according to the sign conventions now, when the shear force, that is the vertical force, when it is acting on the beam, if the effect of the beam is such a way that if the left hand portion of the beam is in upward directions, the effect of that force, the left hand portion of the beam is upward directions, that force is treated as a positive force. Here, if you take this example here now, the force at a B point it is there. Because of this force B, the portion of the beam is always try to move upward directions, or in other words, the left hand side portion of the beam is lower positions and right hand portion of the beam is upward directions. Hence, this force is treated as a negative force now. Say at C point 1000 newtons is acting. When you are considering XX position now, that means this force is nothing but tends to move the portion of the body which lies between XB in downward directions by keeping AX in upward directions. Hence, this force is treated as positive force now. Or in other words, the forces which are acting downward directions are treated as positive with respect to the left hand side reference point. The forces which are acting upward direction are treated as the negative forces. Similarly, the bending moment. A section where the bending moment is such that it tends to bend the beam at the point to a curvature, have a concavity at the top as shown in figure is taken as positive now. Here I am taking the example now. This is the one beam. it is known as a cantilever beam. The force is acting on it now. The effect of this force, the beam deflects this in the directions like this as shown in figure now. Like this. When the forces are acting, it moves. That is, it is treated as now convexity at the top position now. This type of bending is treated as here negative bending now. But if you take another one now, here it is two forces are there now. One more force. Because of this force, it is a bending here this direction. That is the concavity is at the top position now. So this movement is treated as a positive now. This effect is treated as a sagging. This is treated as a sagging. Sagging is nothing but here now convexity at the top. Sagging means here convexity at the top, and sagging means concave at the top now. So this effect is treated as positive forces now. Now the important of finding the shear force and bend moment diagrams now. Here the shear force at any section is the unbalanced vertical forces which are acting toward the left side or right side of the section with respect to the given point. So we have to draw if you draw the diagram which is showing the shear forces are acting on the beam entire its length, that diagram is known as a shear force diagram. Similarly, entire its length at various positions, the bending moment which is acting on the object, if it is represented, that diagram is known as a bending moment diagrams. This bending moment diagrams and shear force diagrams are most important for the design of machine members. So here the shear force and the bending moment diagram, here when we are drawing the bending moment diagram as well as the shear force diagram, the length of the beam is treated as ordinate, and the bending moment as well as the shear force that is represented as here in ordinate, and length of the beam as abscissa as shown in figure now. Okay, while drawing the shear force and bending moment diagram, all the positive, that is here while writing, all the values, that positive values generally represented above the reference line, and negative values below it now. Now, while drawing shear force and bending moment diagram, consider the left or right hand portion of the beam as a reference point. While drawing shear force diagram, add the forces normal to the beam on one of the portions, that is from right portion of the section, from the right side. The forces on the right portions acting downward direction is treated as a positive, while the forces which are acting upward direction is treated as a negative now. Here I am taking here one beam. The forces are acting like this. I may assume the forces which are acting in downward directions are treated as positive, upward treated as negative. So here the resultant of forces we have to take at any point that give the unbalanced vertical force which is acting on the beam. So at the various sections, after finding numerical values, if we plot that shear force as the ordinate and length of the beam as abscissa, then the diagram is known as shear force diagram. Similarly, calculate the bending moment at various portion of the beam. Various portion. If you plot the bending moment as ordinate and join all the points according to the load which is acting, point loads or uniformly distributed load or gradually varying load, that diagram is known as bending moment diagram. Here the bending moment for the point load, generally the bending moment, it depends upon force into distance, hence it follows the inclined straight lines. Sometimes it is also called straight line law. When it is subjected to uniformly distributed load, here I am taking example of here beam reacting. Generally it is represented as W per meter. At free end, the bending moment is 0. At a distance of x here now, the bending moment is equal to total load which is acting, that moment created by the load which is acting toward the right hand side of the portions. Total load is equal to W into x, but it is acting at a distance of x by 2 in the middle. Here it is equal to Wx square by 2 now. So it is having, again, the effect is now, it is on the hanging, hence it is treated as a negative bending moment now. But this curve is there now, joining. This, since it depends upon the square of the distance, it is known as a parabolic curve now. But when the beam is subjected to gradual uniformly varying load, the bending moment depends upon the cube of the distance between the points considered. Hence, the curve is now changing, the bending moment is changing according to the cubic line. The bending moment is always 0 at the free end, or the supports which are freely supported to the beam. And for the simple supported beam, the maximum values depends upon the vertical forces which are acting on it. For example, I am taking, it is a cantilever beam with a point load it is given at a free end. Here the bending moment, the shear force at a point B is equal to W, as shown in figure. But at a distance of x, the unbalanced force from the left or right hand portion of the beam we have to consider. When we are considering right hand side portion, the unbalanced force is equal to only W. That is, it is acting in downward directions, hence it is treated as positive. This we are moving from B to A position now. The unbalanced force which is acting the beam remains constant with the W. Hence, for plotting shear force diagram, first of all, after drawing the simple supported beam and representing all the forces which are acting on it, draw the vertical lines downward directions to represent the various sections of the beam like this, and draw horizontal lines to represent the length of the beam as x-axis. And at B position now, that is the unbalanced vertical force is called W, it is a positive. This is, you have to draw, you have to represent according to the certain scale now, W. Since as we are moving from B to A position, the shear force is constant, hence draw the horizontal lines. This is the representing the distribution of shear force along the length of the beam now. Similarly, bending moment is equal to, it is a moment created by the force at a given point. Here, at this position now, at B position, since the B position is a free end, the bending moment is equal to 0, it is there now. At X position now, the bending moment is equal to force into distance, W into X. But W into X is there now. The effect of the beam is having a hanging effect. According to the earlier convention representation, it is treated as negative values. Hence, down the reference lines, just mark W into X. After that, at A position, again the bending moment is equal to W into L. Here it is equal to W into L. Since the bending moment is varying from B to A position, it depends upon the force into distance. Since B force is a constant now, hence it varying only the distance, hence it the following inclined straight line law like this now. Now based on shear force and bending moment of diagram for the cantilever, here one more problem is here we are taking. Draw the shear force and bending moment diagram for the cantilever beam, a span 1.5 meters length, carrying point to W1, 1.5 kilonewtons as shown in figure at B now. Okay, this is known as here now the space diagram for the cantilever beam, that is representing the length as well as the various forces are acting on it. Here W is given, that is the force is equal to 1.5 kilonewtons, it's acting at B position is given now. So in order to draw the shear force and bending moment diagram, first of all draw the vertical lines passing through the sections of the given beam now. Draw horizontal lines. Since the shear force is positive for the cantilever beam, because all the forces which are acting according to that figure is the downward directions with respect to the left hand side, and so they are considered as positive forces. Okay, to B, nothing but W force is acting downward direction to the positive force. So represent that value is 1.5 kilonewtons. According to the scales, better to take 1 kilonewton is equal to 10 mm. So 15 mm, just draw vertical now. Here it is represent now. As we are moving from B to X position now, the shear force, there is no force is acting on it. Hence the unbalanced vertical force is equal to W 1.5. Hence draw the horizontal line now. Again, moving from X to A position now, the unbalanced force is only W there now. Hence, draw the horizontal lines such that it meets the vertical line passing through point A now. This diagram is known as a shear force diagram. If the shear force is positive, just draw the vertical lines upward direction with respect to the line AB now. That is the reference line now. The bending moment it is there now. The bending moment here, it is a moment created by the force, depending on its effect on the beam. If it is a hugging, that negative bending moment it is called. If it is a sagging, it is treated as a positive bending moment. But here, the bending moment is nothing but in the form of here, it is there like this. Hence, this effect is called here hugging effect. The bending moment is treated as a negative values now. Hence, for the cantilever beam, the bending moment is always negative now. So the bending moment at free end is equal to 0. At distance of x is equal to force into distance, that is the W into x. It is there. So that nothing but here W into x. When we are moving at end position now, the bending moment is equal to force into distance again. That 1.5 into length of the beam is also equal to 1.5. It is equal to 2.25 now. So join this 2.25 according to the scale reference now. Just join by using straight lines because it depends upon the length of the beam now. When the beam is subjected to uniformly distributed load, here we are considering a cantilever beam of length AB, of length L, carrying uniformly distributed load as shown in figure. Here the load is equal to W per unit length. Okay, for this beam, at any position now, the shear force is equal to unbalanced force is equal to W into X is there now. That means when we are moving just from B to A position now, the magnitude of shear force which is acting on the beam, it varies on X values only now. Hence when X is equal to 0, that is at B position now, that is the shear force is equal to 0. At end position, the shear force is equal to W into L now. So join the points this by using the straight line law now. Since these forces are acting downward direction with respect to the point A, hence this diagram is treated as positive value. The second one is bending moment. The bending moment at free end at B is equal to 0. At a distance of x is equal to force into distance required. Force is equal to W into x. The distance means since it is uniformly distributed, the point of action of this force is at the center of gravity. That means in the middle. That is at a distance of x by 2 now. That means the bending moment at a distance of x is equal to W into x by 2, which is also equal to Wx square by 2 values now. Since it values depends upon the square of the distance between the points B and X, this curve is known as a parabolic curve now. Similarly, the bending moment at a point A is equal to, that is other end of the beam, it is equal to W into X by 2, which is equal to W into L by 2, or WL square by 2 now. The effect of this force is the beam deflects in the form of hugging. Hence, that is treated as a negative now. So draw the vertical line downward directions and draw the lines by using parabolic curve. This curve is representing bending moment diagram, or in other words, just to give the distribution of bending moment over the length of the beam. Okay, we are taking one more problem now to explain the effect of shear force and bending moment diagram on a cantilever. A cantilever beam of length 2 meters carries uniformly distributed load of 1.5 kilonewtons meter, run over whole length of and point load of 20 kilonewtons at a distance of 0.5 meters from the end as shown in figure. Draw the shear force and the bending moment diagrams. For in this problem, the given data is length of the cantilever beam is given 2 meters. The point load is given is 2 kilonewtons acting at a point C, that is at a distance of 0.5 meters from B as shown in figure, and the uniformly distributed load that is acting entire the length of the span at the rate of 1.5 kilonewtons per meter. So first of all, we are drawing the shear force now. The shear force at B position is equal to 0, because shear force is equal to, we are taking W into X now. That is W, where W is representing the rate at which the load is acting on it. That is newtons per meter now. It is given. So here X is equal to 0 means at B is equal to 0. It is given. At C position now, the value is equal to W into X. That W is equal to 1.5 kilonewtons, because it is given at the rate of 1.5 kilonewtons per meter. Length is given 0.5. It is equal to 0.7 kilonewton is given now. So this is nothing but equal to 0.7 now. So in order to draw the shear force and bending moment diagram, first of all, draw the lines passing through points B, C, A as shown in figure. Take horizontal lines. Since the shear force diagram for the cantilever beam is a positive, hence take this reference 0.7 at the top. Join B and D with the straight lines, because the shear force is varying with the distance now, because of uniformly distributed load. At C position, 2 kilonewtons is acting at a point load. That is suddenly the values increases to D to C position as shown in figure. The bending moment, the shear force at A position now, it is equal to FA. We take, that is the total unbalanced forces which are acting on the beam. Have to consider. So it is equal to the total length of the beam is 2 meters. 2 meters. The load is acting at 1.5. This is nothing but the total uniformly distributed load is equal to 2 into 1.5 plus 3, nothing but here point load is acting at point C. The total it is equal to 3 2 into 1.5. It is equal to 3 plus here point load is equal to only 2 now. 2, the totally 5 kilonewtons it is acting at. So you have to join these points with the straight lines. This is known as the shear force diagram. The bending moment diagrams, since it is negative, first of all draw the here length of the beam AB as the x coordinate, x axis. At B position it is 0. At C position now, that is bending moment at C is equal to W into x total load, but it is acting at a distance of x by 2. This is nothing but bending moment at C position now. W is equal to that uniform rate of uniform distributed load, which is equal to 1.5 kilonewtons. The distance is equal to 0.5, but it is acting at a distance of 0.5 by 2 now. That is, it is treated as values is equal to 0.1875. This is the values now. That is, the distance is equal to, so you have to take vertical lines, which is representing 0.1875 Newton per meter. Join B and C, since it depends upon the square of the distance, that is W x square by 2. And so join these points by using parabolic curve now. At A point, that is bending moment at A is equal to, we can take W into x square by 2, W into x by 2. That is for the uniformly distributed load. The point load is also at T now. That is, here it is equal to W1 into L is required now. That is the distance between these 2 points now. So according to this calculation now, the bending moment at a point A is equal to W is equal to 1.5. The length is nothing but it is given 2 meters length, but it is acting in the middle, that is 2 by 2 plus point load is equal to W1 is equal to 2 into at a distance of 1.5 now. So totally it is equal to 6 now. So draw the vertical line 6 in downward directions. Join the points again by the smooth curve. This curve is called here parabolic curve. Okay, this is the way of drawing the shear force as well as the bending moment diagrams for the beams now. So the important is we can estimate the magnitude of as well as the magnitude of shear force as well as the bending moment diagram at any section. So we can study what is their effect now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.